So what does it mean for a multivariable function to be differentiable? Okay, let's go back to the idea. Let's go back to all the way back to Calc 1, back to a function of one variable. What does it mean for something to be differentiable? Well, the sort of, oops, I just swiped off my board. There's too much moisture in here. What's the original classic definition of the derivative, or what it means for something to be differentiable of one variable function? Let's go back to that. And we'd say that f prime of x, you've seen this a million times, is the limit as, let's say, h goes to 0 of f of x plus h minus f of x divided by h. Seen it a million times, talked about it, you know what it means, you've thought about it. I want to rewrite this though, and I want to rewrite it to motivate something. Uh-oh, it looks like the camera's going out of focus. Come on, camera, don't do that to me. There we go. This may seem like a rather strange thing to do, but let's multiply both sides by h. And you might wonder for a second, what do I mean multiply by h? Because I've got this limit here. Well, just let it slide for a minute. We can talk about that. But I'll write it like this: h f prime of x equals, and not only that, I in a second I want to get rid of, why does this camera keep going out of focus? It's not good signing. I want to get rid of this limit here in a second, so maybe I'll do it right now. And you should complain, of course. I can't just arbitrarily get rid of this limit. Well, what's the idea with a limit? If h is sufficiently close to 0, then this whole quantity right here is pretty close to this quantity. So just imagine for a minute that h is really, really close to 0. That wouldn't be an equal sign there. That would be an approximately equal sign. Nonetheless, I could multiply both sides by h, and I would get this. But remember, that would just be approximately equal. So what's going on here is that we would have some sort of an error. So I'm going to write this as a capital E, some sort of error function. And that would, in fact, be a function of h. And again, you can imagine as h is closer to 0, the amount by which we're off, the error, would be less and less and less. Now, in some ways, you could look at this as sort of an alternate, well, I'm going to look at this as an alternate way of defining what it means for a function to be differentiable. I want to get this f of x right here, this f of x, and this right here on opposite sides from each other. So what I really want to do is to write this down. I want to write f of x plus h is equal to f of x. Now, if I did that, what way would I be looking? I guess I'd be adding this to both sides. And then plus, I wrote it like this, and for reasons you'll see in a second, most people would probably write it the other way, but it doesn't matter, so we'll write it like that. And then plus some error. Now, this would be minus the error, but I don't know whether the error is positive or negative, so I can do this without any loss of generality. Okay, technically these are not the same errors, but we just rewrite the error functions. What is this telling me right here? This is telling me that the value of a function at a place just a little bit removed from x is equal to the value of the function at x plus, what does this represent? Well, if we think of this as slope, and this is a small change in x. And what is slope times a small change in x? What is slope? Rise over run times a little run. The runs cancel out, you get the rise. This right here just represents the small change in y compared to here. But then there's a bit of an error. Now again, this is something you should have seen before, thought about before. I just want to call your attention to this as a slightly different way of saying what it means for something to be differentiable, but I haven't quite done that yet. There's one other thing that we have to require. The other thing we have to require is the following. We have to require that the limit of the error divided by h as h goes to 0 is equal to 0. Now, what is this? Why do we have this condition right here? The quick intuitive answer is we want this error to approach 0 very quickly. And what happens when that is the case? It means that we're approximating our function here really with the equation of a line. If you look at it right, y equals mx plus b, that's the m. That's sort of the x. That's why a minute ago I said you could write it like that. But at any rate, we require this to be the case. It's not even enough that the error goes to 0, but the error divided by how far we've moved away from the original point goes to 0. So you can think of this as the error goes to 0 very, very rapidly. Now, we want to use this format. We want to use this format to define, notice, not prove, not derive, but define what it means for a function of more than one variable to be differentiable. So let me, I want to write down the definition in the book. I don't remember the definition. Let's see, where do they have it here? This is in 4.4. So if you look in the textbook in 4.4, section 4.4, and it is definition 4.26. So definition 4.26. This definition is exactly analogous to this. And there is I think, a fairly significant typo in the textbook. So warning. I mean, whatever, it's just a typo, so in a way it's not a particularly big deal, but it could be pretty darn confusing. So I need this space right here. But if you see this format right here, it's saying that you can evaluate the value of a function nearby a point where you know the value of the function by approximating it as a straight line plus a small error. And we stipulate that the error goes to 0 very fast. So I want to go ahead and write this definition down and then do a problem with it, okay? So here's in the book, it says a function f of xy is differentiable at a point if for all points in a disk around P, we can write, and here's where the typos in the book. The book wrote down f of x, y, z. That's not what should be there. This is what should be there, like this. Okay, like that. So we're going to say a function f of x, y. I mean, I'm not writing all these words. You can see it in the book there, but this is equal to f of x. Yeah, we're using a specific point. So again, you may want to look at this definition. So we're assuming the point x sub 0, y sub 0. That's the given point. F is the given function. So in other words, if we move away a small amount, we can find the value of that function is equal to the original value plus the partial of f in the x direction, evaluated x sub 0, y sub 0. I hope this isn't going to run through the glare here, but at any rate, times x minus x sub 0. Here, well, you have that written down, so I'm going to cross this out here. Plus the partial in the y direction. I've got to watch out. Oh, this is, this is one way to write it. Another way to write it, I'm not sure which way I like better. The other way to write it, you can do this. Evaluate it at the point x sub 0, y sub 0. I'll go with the book's way of doing it. This is the book's way of doing it. You'll see it different, written differently in different books, but the partial derivative of f with respect to y evaluated x sub 0, y sub 0 times y minus y sub 0 plus an error, which is a function of xy. The idea there is that how far away from the given point we are will determine how great the error is. But if you look at that final condition, the condition of something for a function. The condition for a function to be differentiable, which is to say the function is differentiable, I just repeated myself, is the following: is that the limit of the error divided by this. Actually, it's delta x, delta y, sorry, but I'll write it like this. X minus x sub 0 squared plus y minus y sub 0 squared as x, y approaches x sub 0, x sub naught, y sub naught. And this is exactly analogous to the one-dimensional case. Now, what does this ensure? Again, analogous to the one-dimensional case. One variable case. The graph exists in E2. A differentiable function does not only not have breaks, gaps, or jumps, so it's continuous, but it's smooth in the sense that there's no sharp corners. And this guarantees the same sort of thing. So there's no corners, or I think I tried to do something with a piece of paper maybe last week or 2 weeks ago. There's no creases or sort of wrinkles with sharp, either a sharp corner or a ridge, a sharp ridge. So we don't have anything like that. So it's smooth, really, in the intuitive sense of something being smooth. You wouldn't feel a sharp ridge anywhere. Now, it turns out that if a function is differentiable, it is continuous. We saw an example where something was, the partial derivatives existed, but the function was not continuous. So just because the partial derivatives exist does not mean that the function is continuous. And the theorem in this section, maybe the main theorem, is that if the partial derivatives exist and are continuous, then it guarantees the function is differentiable. But let me work a problem. Hopefully they chose numbers wisely here. So let me just go ahead and do the first example 2.4 in the book. And it says, show that, and they give us a function, is differentiable. So what do we have to do to show something's differentiable? Here's what we have to do. We have to basically determine what the error is. And after we do that, we have to show that this limit, I didn't even write that down, this limit equals 0. So again, to show something's differentiable using the definition, we have to first determine the error, and then we have to show that this limit equals 0. So let's go ahead and do that. Maybe I'll leave all that up there. Let me erase this to get that out of the way. Here. We can write this plus the error. Just leave it like that. So this example, the function is 2x squared minus 4y. Okay, so 2x squared minus 4y. Now, how on earth am I going to figure out the error? It must be the given point at the point 2 comma negative 3. 2 comma negative 3. Well, look, we can calculate this. We can't calculate that. That's the formula. That's the function. We can calculate this. We can determine the partial derivative and then evaluate at that point. Plug in, evaluate the partial derivative at that point, plug in. In other words, everything else here will be known, or will be an explicit formula involving x and y, and then we solve for e. So that's part one. Then we're going to have to try to evaluate that limit. Okay, but the first part shouldn't be bad. A little bit long and drawn out, but shouldn't be that bad. So the function right here, look at this right here. This is 2x squared minus 4y equals f evaluated at that point. Let's go ahead and evaluate at that point. Let's see if I put a 2 in here. Hope I don't mess this up, right? I'm going to put a 2 in there. 4, 8. So we'd have 8 plus 12. So that's 20. Why do I feel like I just did that calculation wrong? Put a 2 in there. Squares 4 times 2 is 8. Plus 12 is 20. Okay. Plus, what's the partial derivative of f with respect to x? Well, that would just be what, 4x? It would just be 4x. So evaluated at this point right here, it should be just 8 times x minus 2. So this chunk right here is this. It's pretty risky me not writing all those in-between details down, but what's the partial of f with respect to y? Well, that's pretty nice. It's just negative 4. So it doesn't even matter what point that's at. So negative 4 times y plus 3 because it's y minus negative 3. So what do we want to do now is simplify and solve for e. So let's see, what does that leave e as? Let's get everything over on this side. We'll leave e by itself. So 2x squared minus 4y. Minus 20. Let's go ahead and multiply everything out. Remember, again, I am leaving e here, and I'm bringing everything else over on this side. That's why it's a minus 20. That would be 8x, but negative 8x, negative 16 plus 16, plus 4y, plus 12. You can double check I did all that right. So the error is a function of x and y, is equal to, let's see, what do we have? X squared terms, 2x squared, and negative 8x. And what do we have? Negative 4y plus 4y. That's gone. That's kind of nice. Wait, so I took care of that. We took care of this, and this. Negative 20 plus 16 is negative 4 plus that plus 12 is 8. So there's our error. Now we're not done. We have to evaluate the limit as x and y approach this point. Well, the limit of what? The limit of the error divided by the magnitude of the vector xy. So what does that look like? It looks like 2x squared minus 8x plus 8 divided by the square root of, well, again, I'm thinking about what am I doing in terms of evaluating this limit. It's the value of the error divided by how far away from the given point we moved. So that's a good old distance formula. So that would be x minus 2 squared plus y minus negative 3, so plus 3 squared. We need to evaluate this limit here. Let me go ahead and write it down. The limit as x comma y approaches the point 2 comma negative 3. Now we have to show, if it's differentiable, we have to show that equals 0. Okay, so here's part 1 is getting up to here. Part 2 can actually be the trickier part because you have to evaluate a limit. And so you may need to, who knows what, algebraic trickery or trigonometric trickery may be involved. Let's see, how can we try to evaluate this? Well, let's see, what do you do when you're not sure what to do? Is try to simplify things. Up top here, well, it occurs to me at least we could factor on a 2. That hardly seems like anything worthwhile doing, but let's do it anyways. 2, we get x squared minus 4x plus 4, and all that's still divided by this. Now this is just me messing around with the algebra, hoping I can simplify something. You've spent the better part of your mathematical lives factoring quadratic polynomials. So again, when you see one, if you're not sure what to do, I don't know, try factoring it. And that definitely is factorable. So this is equal to 2 times x minus 2 squared divided by the square root of x minus 2 squared plus y, plus 3 squared. Now, you look at this and you think to yourself, or you should think to yourself, this would be so fantastic if that term wasn't there. Because if that term wasn't there, look what you'd have down here. You'd have the square root of this squared. So you'd have x minus 2. This would cancel with one of these. And then you could evaluate the limit just like that. Nothing to it. Except this term is here. But think for a minute what we're trying to do. We're trying to show that this limit is 0. So I don't know what else to say except I see to do this. This is less than, or really less than or equal to, the following. Divided by because all this term here could do would be to increase the denominator. And if you increase a denominator, you make something smaller. All these terms are positive because those all get squared. Well, look at this right here. What is this equal to? This is pretty awkward there, I'm writing this, but what is this equal to? when you do the obvious algebra that I just mentioned a minute ago, you get this. Well, what's the limit of this is look over there. We need x to approach 2 and y to approach -3. There's no y here, so that doesn't concern us. But as x approaches 2, we can just put a 2 in there. So in fact, this limit is 0. So in showing that something is differentiable, well, first off, what are you doing? You're showing that it's smooth. Really, in our intuitive sense of the word, no sharp points, no creases. But how do you do it? You have to use this definition, plug in everything, solve for e, set up this limit, and then hope you can evaluate that limit. Now, in this context right here, nobody's, I don't think, is trying to give you a epically difficult limit to evaluate. That's not really the point here. But then again, who knows what skills you might need? Okay, so that's what it means for a function to be differentiable. And this is a pretty good problem. Now that you see this definition, again, it's fairly mechanical. You see what to do, and you get a nice answer. Okay, so I'm going to end this video here and come back with another one in a minute.